All right, here we go. We are talking chapter 4, sections 1 through 3, discuss Newton's laws of motion.
Oh my gosh, I know. You love Newton.
Newton's laws cover all of the different things that we need to discuss about how motion becomes free body diagrams or can be modeled by free body diagrams. They also talk about why we can set certain situations equal to other situations given very little information as far as vector physics is concerned. So Newton's laws of motion are a further application, if you will, of the kinematics formulas. The first law is that of inertia. And inertia just states that when A is 0, an object is either in motion constant or at rest. When something starts moving, it's going to stay moving. It also tells us that in this particular situation, the net force on that object is going to be 0 because the acceleration is 0. We know that the net force on that object also has to be 0. The object is moving in a constant manner. Constant meaning the same speed or no speed. Okay. The second law then is how force is related to mass and acceleration. Okay. So an object that is changing its speed has an acceleration, and that acceleration is going to be related to its mass as well as the net force on the object. Newton's third law then is equal and opposite forces. So every push has a pull. Etc. Okay. Also in chapter 4, we developed the free body diagram. Where we model systems as single points. From which all forces apply. So in other words, if this is my system could be anything from a planet down to an atom. That system has forces that can be applied to it. And then we talked about native forces or common forces. Ooh, that glare though. Day. All right. So, then we talk about common forces. Still chapter 4. And there are 3. The first one is weight, which is mass times gravity. This is always going to act downward compared to the system's location. And we'll see what that means here in a second. So this is number 1. Number 2 is the normal. And the last one is going to be friction. Which acts to oppose motion's direction. We're going to start next semester with a very intense dialogue on friction and types of friction. So when it comes down to it, friction is always just going to be acting opposite of whatever the direction of the motion is. We talked about friction on surfaces. We have investigated, but for the most part, ignored friction as air resistance. So we've kind of talked about it. We can insert air resistance and just call it a type of friction, as long as we understand that friction always acts opposing motion. Okay? So those were our common forces. Other forces that were discussed. Tension. Typically in ropes or elastic situations. Tension will be present when something is hanging. Sometimes it's going to be equal to W when the situation is a object just hangs. Or we have what we call tightrope situation. That tightrope situation is the tension equals that.
Say
W over 2 sine theta. W being, of course, mg, so if you want to, you can. These two formulas, the weight formula and the tension formula, are given on your final exam. The T equals mg over 2 sine theta. Okay, so this guy will be given. This guy will be given. Make sure you know when to apply and when not to. Specifically this situation versus this situation in chapter 4. Okay. All right. From there, we talk about applying Newton's laws of motion. So let's look at a situation where we've got a block on a 25-degree incline. We've got the mass of the block is 35 kilograms. I reserve the right to give you more information if I need to, but at the moment I think I've got it all. Okay. So, if this is our situation, what's the first thing we should aim to do?
Components?
Free body diagram. Okay? Let's diagram the situation first. And then, yes, we are going to work on components. Okay. So I'm going to make the block a single point. I'm going to draw my normal. Remember that normal acts opposite of the object's surface, so acts the perpendicular to the surface. Weight is going to act straight down, because that's what's pulling it. the angle it's being pulled down with is equal to the angle of the incline. And in this particular diagram, does it say that we have a friction force?
No.
In fact, it says no friction. So should I be drawing anything else? Or is that good? That's everything, right? Yeah.
I'm a little confused on that angle part of it. How do you know that it goes there?
Oh, that's just it's like if you, is like basically what they're saying is this is the angle is 25 degrees. It's just like something to commit to memory is whatever the incline angle is going to be the angle on the inside of the triangle where weight will be. You could probably prove it yourself if you really wanted to, but I would say just try to commit to memory that if you're on an angle, this is what happens. Okay, so here's what we've got, right? Now, what do we do next?
Components.
Let's do some components. I would also argue that you could flip your diagram so that normal points straight up, because remember we want everything on x and y axes. So that's what I'm going to do first, but then yes, we are going to work on components. So I'm going to shift this and make sure that I know which direction the W is still pointing. Okay, so next thing I'm going to do is I'm going to take this triangle and I'm going to solve this. And remember that we do W parallel and W perpendicular in these cases because we don't want to say X and Y in the case that we just kind of forget that we actually have to analyze the triangle first. Okay, so we're going to look at our triangle and we're going to recognize the angle is here. If I want this is W parallel. Okay, the W parallel formula in this case is opposite, which is sine, correct? So this should equal W sine of theta. And then of course, because this one is perpendicular, it's going to be cosine. So always make sure you're analyzing your triangle for that trig. Don't just assume one is this and one is this. It really will be situationally dependent. Okay. All right, so I'm going to plug in numbers. So W parallel is going to be mg times the sine of 25 degrees. M was given as 35. And G is 9.81 or 9.8. W perpendicular is going to be mg times cosine of 25 degrees. Don't forget to be in degree mode in your calculator.
That's the problem. That's a big degree. I got 144.9.
For which one? This guy?
Yeah.
Okay. Well, 35 times 9 is pretty big, so that makes
Oh,
sense.
yeah.
So 144.9.
Yeah.
Remember that these are forces, so they get the unit of newtons. And then what'd you get for the other one?
310.8.
Okay. There's no frame of reference for saying these are wrong, right? In our particular case, weight is mass times gravity. So if your mass is, I mean, the mass of a human being is anywhere between 60 and 100 kilograms, right? So this isn't necessarily bad. It's fine. Okay, so from there, I'm going to draw another free body diagram because I need to analyze those for the Newton's law situations. I'm looking for F net situations, right? So I'm going to draw again. I'm going to draw my final free body diagram that puts everything on an axis.
Why are you able to do that?
Because we just broke down this one,
And then you just like flipped it?
and then I had turned it, and then I solved for components so that I could have x's and y's.
Oh, okay.
I want everything on an axis, always with free body diagrams, okay? And that's because the next thing we do is talk about F net. Okay, so I'm going to rewrite this over here so we have the information.
Your board's erasing good today.
It's because I leave stuff up on this one so that they can't touch it.
Oh.
And this is the one I filmed this
That's
class
smart.
videos on, so. All right, so now let's analyze for fnet x and fnet y. So first, let's identify the situation. If it's 0 or m times a, that what we're looking for is the thing changing direction in one direction versus the other? Yes. Do you know where they are? If she needs more, just let me know. I can find the rest of them.
Okay.
Okay. So fnet and the x. Let's do fnet y first. So let's look at the y-axis. So what do we know about this thing in the y direction? Is it moving in the y direction? No. So what should we put here?
0.
0. Okay? That's the first thing. And we are going to do it again. So this is the analysis of the situation. Let's say that. And then this is the free body diagram analysis. In other words, we're going to put forces over here for the fnet equations. And over here, we're just going to say, is it 0 or is it ma? Okay? So what's this one going to be then? In the x direction. Is there anything opposing the one vector?
No.
No, there's no friction. So this one's going to be moving to the left. Since it's moving to the left, is it possible that a should be negative? Yes, because of the way we define negative and positive in our situations, right? Okay, well then what is fnet x going to equal? Just using forces on the diagram. This is what we're doing. Remember that up is positive, down is negative, left is negative, right is positive. So for this guy, let's do y first. What would we write for the expression?
N times W
We would do
parallel.
n minus w perpendicular.
Oh.
Okay? This is the part where we really find a disconnect. This is the thing that I've identified you guys are really disconnecting with. So you want to practice these things, writing the expressions. What about fnet x? What are we going to write?
W parallel.
Well, we're going to write negative w parallel, right?
Oh, because on the left.
Because it's going to the left. Don't lose our coordinate system. Yes, it's the only one that's happening in this particular direction, but don't lose your coordinate system. If you put the negative in front, it means A will end up negative. And we want A to be negative because we want to indicate that acceleration is happening to the left. Okay? So we have to be consistent with our values. All right, so now what do?
Plug in chug.
Now we set them equal.
Oh.
Right? We set each side equal to what we've done. We know that this is the same variable, right?
Yeah.
These are the same variables, so can't we just set these two things equal?
Yes, you can.
Okay, so we're going to do
So funny.
MA equals negative W parallel, and then we're going to do 0 equals N minus W perpendicular. And this is going to set us up for both A and B because I asked you what is A and what is N.
Okay.
So we have to solve both of these expressions that we've just come up with for something. Which one do you want to do first?
X.
You want to do F net X?
Sure.
Okay, so let's solve. MA equals W parallel. Oops, negative W parallel. Don't forget that. We have a value for W parallel, don't we? So we just have to plug that number in. So we're going to do negative 144.9 equals times our mass, which is 35. What do we go for this one? And don't forget that the unit is meters per second squared. What we got for W perpendicular? We're going to do 0 equals N minus 310.9. oops, 0.8. So N just equals, yep.
Yo, my hair looks ratchet.
Now, real quick, should normal be positive? Look at your diagram.
Yes.
Absolutely, right? Okay,
Is it because it's like up?
because it's pointing up. So that was the most complicated free body diagram we really talked about. Now, what happens if I add friction to this situation?
Oh,
We add a vector, right?
so what would you?
How would you,
How would you
pose
find
that?
components then?
Yeah.
Do you find components for?
Well, so remember that if we had friction, it acts opposite of the surface. So you wouldn't have to. In the diagram, it just flips when you change
Oh,
it.
like the
Remember,
W-
it's like 90 degrees. It's a perpendicular force to normal
Okay.
in that particular case. Because it would be, friction is always according to the contact of the surface.
So,
Always.
so would your components still be the same?
So your components would change slightly, right? You would still have this diagram. So what happens to this? This one becomes that. Make sense?
Would you give us friction or would you have
You would have to have friction or acceleration in that situation to calculate friction. Remember, you can only solve for one variable at a time. So you'd have to have one more thing given. We just want to talk about what happens with friction. Yes, ma'am.
I guess this doesn't really have anything to do with this problem, but what are the specific like circumstances you need in order to use T equals W or T equals mg divided by 2?
Yeah, we can do some tension problem attacks. Yeah, let's do that. All right, so let's talk about T equals mg first. That's a hanging rope situation. That's a situation where maybe we have let's say there's a bar that is suspended. It's got a person or two. Here we go. Let's talk about, like window washers on high rises.
Yeah.
Let's talk about that situation. Cool. All right, so here's one situation where tension will equal weight. In this particular case, though, there's two ropes. So there's two tensions. So this is the first free body diagram I would expect you to draw, okay? The second one that I would anticipate puts them together and opposes W.
Aren't they equal?
If the object is not moving, what do we know about Newton's second law?
0.
Yeah. So, if the object is not moving, F net is 0, and in this particular case, we're talking Y only, right? Okay. Well, what's the expression you would draw? Or what's the expression you would write? Using the forces.
T2 times T1
Well, T1 plus T2,
oh.
right? They're just on top of each other.
Yeah,
And then minus W.
Wait, what is that? Oh, I figured it out. Okay.
And then we just said F net Y is 0, so we would set the whole thing equal to 0. Now, in this particular case, you'd have to be told something more about tension. You'd have to be told that, right? You'd have to be told that the tensions are equal. Or you'd have to be told that like T1 is 1/2 or whatever, 1/2 of what T2 is. Either way, you'd have to be given some information about what the tensions are in order to plug them in down here. Okay?
Why do you subtract?
So like for instance, I see the confusion face. Okay? Let's say that we were told that since they are closer to this side of the, or I'm sorry, since they're closer to whatever side of the rope, one tension is greater than the other. Okay? Well, then we'd have to plug in something to know. So for instance, down here, we would say, okay, so since 1/2 T1 is T2, that's what tension 2 is, we would change our expression to be this. We'd calculate T1, so T1 would be, with me so far? Okay. From there, we get T1 equals that.
Oh,
Good.
yeah.
And then we would have to plug that into like this to find T2. This is a more complicated tension situation. For the most part, we've dealt with this. But could you theoretically do something along these lines because you know about tensions and you know how forces work? Absolutely. Okay. So what's the situation where that's terrible.
That's where they're.
Yes.
Yeah.
Got a person standing on a trampoline. Let's go trampoline this time. Does it matter if it's not a tightrope? No. What matters is that the person is standing in the middle and that the angle of the tension is the same on both sides. We are not doing uneven tension problems in this class for a reason. Okay? So, if that's the case, this is when you can use the other formula.
Trampolines are so fun.
Anytime you have some kind of sagging tension where the angle is the same on both sides is when you can use the T equals W over 2 sine theta. So person on a trampoline. So there was a problem where you did something with like a spider and her web. The first situation was the spider hanging from her rope. Okay? That was the first situation. In this particular case, there was only T and W to deal with. Okay? So you just did T equals W. The second situation, don't like spiders, had her hanging out on her web. Okay?
Yeah.
Know what I'm talking about?
Yeah.
You had her like chilling on her web, and there was all kinds of cool stuff going on. And it was like, I don't know what spider webs look like, guys. Okay? Because I don't like them, and I make someone else get rid of them. So let's say that she's got like a 15-degree sag. Because she's a big ol' spider. She's causing a big sag in her own web. All right? She's preggo with all the babies, whatever you want to say. That being said, you were given her angle of sag on whatever she was standing on. That would be this situation. Okay? So those are the two situations you really have to anticipate. We've talked about double rope situations before, but really we've just said that like they're identical to each other, so you just add them together. 2T was what it ended up being, I think, with our double ropes. Okay, what other questions do we have? Feeling good?
I'm feeling better.
Can't wait for this to be over.
Yeah.
Yeah.
Finals week starts tomorrow.
All my big finals are